All right, so we're closing out our study of Newton's three laws of motion. We've done first law, we've done second law, and our last one, as you might guess, is the third law of motion, Newton's third law of motion. This law is not as math-based as the previous two. It also takes a little less time to teach, so we don't spend quite as much time on this law. And it is a law that most students recognize when they hear the traditional definition of it. So let's take a look. All of you have, of course, heard the statement, for every action there's an equal and opposite reaction. I prefer not to use that as much. I think it's a little misleading for two reasons. When you hear it the way it's written in a normal textbook, you don't even include the word force in the explanation. You just hear for every action there's an equal and opposite reaction. I prefer that if you're going to use this, that you include the word force at the end of each part. For every action force, there's an equal and opposite reaction force, so that we remind ourselves that this has to do with forces, the action and the reaction. And the second thing is that the statement makes it appear as though one thing happens and then another thing happens, when in actuality they are simultaneous. The forces occur at the exact same time. So when object A exerts a force on object B, at the exact same time, object B exerts an equal and opposite force on object A. It's not as if one thing happens and then this other thing happens. The forces occur at the same time. And a good mathematical way of looking at it is this. The force of object 1 on object 2 is equal to the force on object 2 to object 1. And the reason the negative sign is there is, remember, forces are vector quantities, so we know that they act in different directions. So if one force is in a positive direction, the other force, if it's equal and opposite, has to be in the negative direction. You don't need to put the plus sign, though, in front of the initial F there. These are called Newton's third law force pairs. They're equal and opposite in direction. And again, they do occur simultaneously at the same time. So if you're walking down the hallway, you are pushing against the floor with a certain force, and the floor pushes back on you. So if we're going to write that out, this is the force of you on the floor is equal to the force of the floor on you. And of course, it's in the negative direction. So you may think of it as you pushing yourself down the hall, when actually what's happening is the floor is pushing you down the hall. If you're swimming, you push against the water. Well, the water exerts an equal and opposite force on you. So the way we would write that out is the force of you on the water is equal to the force of the water on you. They occur at the same time. They involve opposite directions. Now remember, when you're swimming and you're trying to move in a forward direction, which way do you tend to move your arms? You move your arms backwards. So as you move them backwards, that propels you forward. And when you're walking down the hallway, which way are you pushing on the floor? You're pushing away from you in a backward direction. Which way do you move? You move forwards, right? So that's the idea. These force pairs are interchangeable. When I say I act and you react, I could rearrange that to say you act and I react. This means the same exact thing, this statement here. So when I write the force of object 2 on object 1 is equal to the force on object 1 on object 2, I could flip these. And I could say the force of object 1 on object 2 is equal to the force of object 2 on object 1. I know it sounds like I'm repeating myself, but if you look closely at the way these are written, they're written kind of in opposite direction. You could also switch the negative sign, depending on which way you want to call negative, left or right, up or down. Again, they are simultaneous, no lag time. So as you are pushing on that water when you're swimming, immediately as you push on the water is pushing you back. As you push on that floor with your feet, as you walk down the hall, the floor is pushing you immediately back. They are equal and opposite. It's the same magnitude. So if there's a 10 Newton force one direction on an object, that other object applies 10 newtons in the opposite direction. And unlike the forces that we examine on the first law, where the forces are acting on the same object, in third law, we talk about the forces acting on different object. So if you have say a book sitting on a table, a poorly constructed table like this one, if we were just going to talk about the force pairs, the third law force pairs, well, the book, there's a force that the book acts on the table. But there's also a force in the other direction that the table applies to the book. So again, we're talking about two different forces here. We're talking about two different objects here. We're talking about the force of the book on the table, but there's also a force of the table on the book. If we were drawing a free body diagram from first law about this book, and we were just focused on the book, we'd say, okay, there's a normal force pushing up, but there's also a force of weight pulling down. And you might think, well, this looks like a force pair. There's two different forces, but these forces, the normal force, the table is acting on the book, and the weight of the book is acting downward. So they're both acting on the book. So this cannot be considered a third law force pair because the forces are both talking about acting on the book. This is a third law pair. But if we say, here's the earth and here's the book, obviously not drawn to scale. The force of the earth on the book is equal and opposite to the force that the book has on the earth. This would be a third law force pair. Earth pulls down on book, book pulls up on earth in an equal and opposite force. This one here is not considered to be a third law force pair. That's just a first law free body diagram. So just to review, if we were doing this first semester and I said to draw a free body diagram for a book sitting, or excuse me, a box sitting on the ground. Well, we know that the earth is pulling on the box in a downward direction. Remember, we always draw our weight vector straight down. And the earth is applying a force to the box in an upward direction. Remember, this is the surface of the earth here, right? And that is pulling in the opposite direction of the weight. But in both cases, the normal force and the weight are both acting on the box. On the box. So we can't call that a third law force pair because third law force pairs have to be acting on two different objects. In this case, we have two forces, but they're acting on the same object, in this case, the book. But let's say you are pushing on the box to the right. So this would represent your force acting on the box. But the box is also exerting a force on you. So you notice that we still have two vectors drawn here, but the vectors apply to different objects. They don't apply to a single object. This is you, the force of you on the box. This force is the box on you. Same forces, same magnitude, opposite direction. So this would be considered a third law force pair. So if we were going to name some action-reaction pairs, some third law force pairs, Usain Bolt running along the track, we could say, and you probably would want to go through this and do it yourself before you watch me do it. So you may want to pause here and go through and pause it and then come back and watch the rest. So Usain Bolt is running along the track. So we have a force of Bolt on the track, but we know that the track also exerts a force on Usain Bolt. So we would say the track force on Bolt. And of course we'd have to be in the negative direction. Now we could put the negative here if we wanted. We wanted to call the negative force to be Bolt on the track. And this would be the same deal here. Thelma high-fiving Louise. Well, let's see. Again, Thelma applies a force to Louise, but Louise applies a force to Thelma. This should be a T right there. Sorry about that. And this is an L, and this is a T. So let me rewrite that. It's kind of confusing. Thelma applies a force to Louise, and Louise applies a force to Thelma. Chuck Norris climbing a rope. So we have Chuck pulling down on the rope, and we have the entire roof caving in because Chuck Norris is awesome. No, I'm kidding. The force of Chuck Norris pulling down on rope, and there's also the rope pulling up on Chuck Norris. And then we have a skydiver falling to the earth. So the skydiver pulls up on earth, and the earth pulls down on skydiver. And then Superman pushing down on the earth, and the earth pushing up on Superman. So it's pretty straightforward. I don't think you'll find these to be very difficult, coming up with these third law force pairs. Just have to remember that one of them is negative, and that means that you have to put the negative sign on one side or the other. It doesn't have to always be on the right. Like I put it on the left up there. That's fine. Well, hopefully by now you realize that the mass obviously plays a role in all this. We know that from some second law that the larger the mass of something, assuming the force stays the same, the less the acceleration is going to be. And the smaller the mass of something, the greater the acceleration is going to be, assuming the force stays the same. So in third law, it's no different. Now, if you take a cannon, for example, you have this cannon, and it's going to be shooting out a cannonball. We know that the force that the cannon exerts on the cannonball is equal to the force that the cannon produces on the cannonball is going to be equal to the force that the cannonball exerts on the cannon. And you think, well, how is that possible? You would think that the forces would be different because the cannonball goes so much farther than the cannon. But it's the acceleration that is different. When the cannon shoots the cannonball, it recoils to a certain point. It does go back a certain way, and the force that cannonball applies to the cannon is the same as the force that the cannon applies to the cannonball. But the acceleration, the change in velocity over time of the cannonball is much greater because the mass of the cannonball is so much smaller than the mass of the cannon. Same thing with the recoil of a rifle. The bullet applies a force to the gun, and the gun applies a force to the bullet. It's the same amount, but the acceleration of the bullet is much greater because the mass of the bullet is so much smaller. This will be a different direction as well. And that's this idea that as a person drops, say, a paper clip towards the floor, the earth applies a force to the paper clip downward. And believe it or not, the paper clip does apply a force to the earth up. But we don't notice a change. We don't notice an acceleration because the mass of the paperclip is so tiny that it can't cause the earth to move very much because the mass of the earth is so much bigger. Now, there's a video, if you watch the PowerPoint version of this instead of my video, there's a video of this dump truck hitting a much smaller car. So I'm sorry that the graphics aren't working, but this truck here ends up hitting a very tiny car here. And the question says, which vehicle experienced the greater force? And the quick answer, the mistake a lot of students make is they want to think, oh, well, the truck is so much bigger that it just has a much greater force on the tiny car. But really what's happening here, guys, is that the force is equal. The force that the truck hits the tiny car with is the same as the force that the tiny car hits the truck with. But because the truck's mass is so much greater, the acceleration on the tinier object, in this case the car, is much greater. So the effects are different. If you're driving down the road and you hit a mosquito and it splats onto your windshield, which object exerts greater force, the mosquito or the car? Well, it's the same. But the mass of the mosquito is so much smaller that it has a greater acceleration than the car does. So, very easy mistake to make, but the force here would be the same. So if you think about space where there is no air, and you have rockets that can adjust their orientation in space, like the International Space Station with these little thrusters that they have on the vehicle, how in the world do these objects move if there's no air to push against? And that's all about third law. The rocket pushes out all of these burning gases, and it's millions and millions of molecules of gases going at thousands and thousands and thousands of miles per hour, pushing down. Well, those millions and millions and millions of molecules going at thousands and thousands of miles per hour, they are very low mass, but there's thousands of them. And if all these thousands and thousands of molecules are pushing, the rocket's pushing them out with a certain force, that these gases apply an equal and opposite force to the rocket. Thus, the rocket gets propelled through the air. You do not have to have the atmosphere to get an object to move. For the longest time, people didn't think space travel was possible because they thought that for something to move, that the air had to push it as it flies through the air. But this is not the case. It's the molecules that are being ejected by the rocket itself that are propelling the rocket through space. So rocket pushes on burning gases, reaction, gases push on rocket. So go through these questions now. We'll go ahead and hit pause and go through these questions and then come back and see if you got them right, answer them. So when a hammer exerts a force on a nail, how does the amount of force compare with that of the nail on the hammer? Again, if you haven't figured it out by now, you're never going to figure it out. It should be pretty common sense. It's the same value. The force that the hammer hits the nail is the same as the nail hitting the hammer. The nail has a much smaller mass, so it accelerates much more than the hammer with a bigger mass accelerates. But the force is the same on both. If the earth pulls you downward against the ground, what is the reaction force? Well, think about it, guys. Earth pulls down on ground. Earth pulls down on you. You pull up on earth. Right? So earth pulls down on you. You pull up on earth. Your mass much smaller compared to the mass of the earth, so we don't see the effects as you would if the earth was a much smaller object. When a cannon is fired, are the forces on the cannonball and the cannon equal in magnitude? They are. Are the accelerations equal? No, they are not equal. According to second law, we know that a smaller mass is going to have a greater acceleration, so that's why the cannonball has a greater acceleration. And then true or false, Newton's first law of pairs act on different objects, and third law of force pairs act on the same object. That is false. Newton's first law of pairs act on the same object. Newton's third law of force pairs act on different objects. This should be 6 and 7 and 8. If you walk on a log that is floating in the water, why does the log move backwards? Well, there's very little friction between the log and the water. So as you push on the log moves backwards because of the force you're applying to it. There's no friction. Let's just imagine that log wasn't on water, it was just on cement. Well, the log wouldn't move. And the same thing happens if you are stepping off a boat onto a pier. It's very easy to fall into the water because you don't think about the boat. As you push off on the boat, it moves away from you because there's very little friction between the boat and the water. What is the reaction force to an action force of 1,000 newtons exerted by the Earth on an orbiting GPS satellite? Well, guys, it's going to be the reaction force of 1,000 newtons, exact same amount, equal and opposite. If the action equals the reaction, why isn't the Earth pulled into orbit around the satellite? Well, again, guys, it's all about the mass here. The Earth's mass is so much greater than the satellite's that there is really no acceleration at all of the Earth. A smart car rear-ends a Mack truck. A tiny object rear-ends a very big object. Upon which vehicle is the force of impact greater? The force of impact is the same on each. Which vehicle sees the greatest acceleration? Well, certainly the smart car would see a greater acceleration here because of its smaller mass.